Let's go. All right. So, and recall that an elliptic curve over a field K is an equation of the form y squared equals x cubed plus ax plus b, such that the discriminant of the equation, which is 4a cubed plus 27b squared, is non-zero. Okay, and last time we showed that the condition delta E being non-zero is equivalent to say that the polynomial, let's call it f, has or has no repeated roots in the algebraic closure of K. But we also had, so this is the so-called algebraic equivalent formulation of this condition, but there is also an equivalent geometric condition that says, at least what we showed last time, that over the real numbers, saying that delta of E is non-zero is the same as saying that E has a tangent line at every point. And this this is usually called in analysis, real valued function analysis, it's called smoothness. Now, actually, when I looked back at the last session, I saw there were some small mistakes, and moreover, what I want to demonstrate today is how to take this geometric condition and make it meaningful over any field instead of the real numbers. And this would, I hope, demonstrate the way of reasoning in algebraic geometry. And along the way, I will repeat the part we did last time on this equivalence to the geometric condition, and correct the mistakes. what I want to start with is what is the tangent line? So in calculus, you have let's say a function, the graph of a function. It doesn't really have to be an actual function. It could be a curve like we have that continues, I don't know, like this. But once you pick a point, the whole discussion is local in the sense that you can look at the graph of the resulting function over some small interval in the x-axis, below or above the point, and whatever you get, I mean, whether there is a derivative or not, does not depend on the rest of the curve. It only depends on a small neighborhood, as small as you like, around this point. So you could take this purple part, and if you don't start with a function, then you can even artificially just complete it to a trivial function like so, and this resulting pink function in this point we are interested, whether it would have a derivative or not, it would capture all the situation we look for. I mean, the purple function will have a derivative at the point P, if and only if the original curve here on the white will have a derivative at P. And derivative, of course, it has a formal definition that people do in calculus. But for us, you can think of it, and this I think is discussed in school mathematics. The derivative at P is like a vector that signifies the direction of the function at this point. And if we accept, so this vector, this is the derivative dy of dx at P. And if we accept this definition of derivative, then it is natural to define the tangent line as follows. So let f x y be, maybe we start with just a polynomial. Polynomial say over k. Oh, you know what? Yeah, okay. So we have a polynomial in two variables over a general field k. And I would like to say that if you give me a point in k times k, so it has an x coordinate and a y coordinate, such that f of p is 0. So P is a point on the curve. Then if dy to dx at P exists, we define the tangent line to f at P as the equation y minus y0 equals m times x minus x0. So what do we make of this definition? This is a general field K, remember. And of course, the case you should always have in mind is when K is equal to the real numbers. And then what we get with the picture is this blue line that, so you could say that the tangent line over the real numbers is the unique line that passes through the point P and has a slope that is and goes exactly in the direction of the function at P. So you can think of it as the best linear approximation of the function in a neighborhood of P. Is this clear? Is this I can explain a bit more if not. Yes.
I'm not sure I understand why we want f at point P to be equal 0, because on the graph above it is not 0.
No, I did not say 0. We say f at P. When I say f at P equals to 0, it means that P is in the solution set of F. So the curve, maybe if you want, we can distinguish. We can call the curve C, but the curve C is the solution set of a polynomial in two variables, fxy equal to 0.
Oh, that means that just P is a point in the curve.
Yes, so P belongs to C.
All right. Okay,
P belongs
thank
to C is saying that f of P is equal to 0 by definition. Yeah, so, but of course the derivative does not have to be 0. The derivative is 0, if you probably remember it from school, when we have a local minimum or a local maximum, right? Like at this point, the derivative would be, I mean, the slope of the tangent line will be 0. So when I try to make this definition, I actually presupposed some basic framework. I mean, namely, what I presupposed is called affine geometry. And in affine geometry, it's like we replace the real numbers with an arbitrary field. Could be, in our case, we would be interested in fields of positive characteristic. And the affine space A n with subindex k is simply k times itself n times. This is also k to the n. And in our case, since we only deal with curves, we need the affine plane. This is A2. A2 is simply k squared. This would be analogous. I mean, this would replace the ambient space r squared that we pictured the curves we have over the real numbers or the general field. And a line in A2 is the solution set of an equation of the form y equals mx plus b, where now m and b are in the field K. So in particular, if K is finite, then of course K square is also finite, and a line in the affine plane, this is the affine plane, a line in the affine plane will be necessarily a finite collection of points. Okay, so what we're doing here is we're taking kind of a leap of faith that things that we want to say about lines only depend on the algebraic description of what I mean of a line as the solution set of a certain polynomial. But as you will see, this can take us quite far. Now, in particular, when we say the derivative dy to dx, the derivative over the real numbers, it can be defined in an analytic way as a certain limit and so on. I don't want to get into it, but what we need here is an algebraic variant. And this is possible due to the fact that we're dealing with polynomials. Polynomials, we can always do formal derivative. So for maybe example, I have, let's say, y squared equals x cubed plus 2x. Then if I want dy to dx, what I need to do is to do what is called implicit derivation. So implicit derivation, I think of y as a function of x, and I derive the left-hand side and the sorry, Lisa, you wanted to ask a question?
Yeah, I wanted to ask about line definition. Does it mean that a line in the definition is a set of point pairs, but geometrically it can be not a line?
There is no geometric, it's a set of pairs, yes, just like if you think of it, also a line in the plane is a set of pairs, right? It's the collection of all pairs,
Right.
right? So yes, but it has no geometric interpretation, at least not anything meaningful or straightforward. Once the field K is I mean is of positive characteristic.
Okay. Okay.
Okay, I mean, of course, you can order this. We discussed it last time. You can order the points 0 up to p minus 1 on the x-axis, 0 up to p minus 1 on the y-axis, and you will have, but you will not get a line. You will get some discrete version of a line up to a certain point. And then things will start to get crazy because you start doing modulo p. I mean, whenever, right? So you will get some scattered scattered plot.
Yeah,
And
makes
this,
sense.
yeah, okay. So for us, a line is simply the solution set of this polynomial in two variables, right? So it's like it's the collection of all x, y in k square, such that sorry. Such that y equals mx plus b. And the next thing I want to talk about after the solution set is the derivation, because in the definition of a tangent line, at least over the real numbers, I use this notion of derivative. And what I do in the general case, I simply derive polynomials in a formal sense. So to do dy to dx in this example, you think of y as a function of x, and you derive both sides with respect to the variable x. When I derive the right-hand side, I simply get 3x squared plus 2. When I derive the left-hand side, well, now I need to, this is like deriving the function y squared is like 2y times the derivative of y with respect to x. And now I can simply divide by 2y and get that dy to dx is 3x squared plus 2 divided by 2y. Okay, so I can always do it for any polynomial. I mean, I just picked random numbers, but I think you can easily believe that this can always be done for the polynomials we care about, which are very very restricted, right? It's like just the cubics of a specific form. But I can play the game also differently. I can, so this would be the analog of the derivative in the sense we talked about over the real numbers. But I could also do dx to dy. How do I do this? Well, I think of x as a function of y, and I derive the left-hand side and the right-hand side with respect to y. So when I derive the left-hand side with respect to y, I simply get 2y. When I derive the right-hand side with respect to y, I get 3x squared times dx to dy plus 2 dx to dy. And so dx to dy, I can isolate it, and it would be 2y over 3x squared plus 2. Now, when I discussed the tangent line, I left an edge case, and the edge case is if you have, in our case, you have an elliptic curve like this, then maybe let's suppose that this is the y-axis. Then this line is, we would like to say that it is tangent to the curve at P, but the slope of this line will be infinity. And indeed, if you try to calculate the derivation of the curve at this point, you will get something divided by 0, so that it's not defined. So how do we deal with this case? I mean, of course, it could be that the derivative doesn't exist for other reasons. I mean, the derivative here is, we would like to say that it's in infinity, and that there is a tangent line. But if I take like a curve like this I think is y squared equals x cubed plus I think plus x, but let me check. And this is plus x squared. So you see, in this curve over the real numbers, we would like to say that there is no well-defined tangent line, or even well-defined derivative at the origin. And the reason is that I may come from this direction, then I think that the tangent line is like this. But if I come from this direction, then the tangent line is like this. So this curve does not have a derivative at the origin 0, 0. And indeed, if I do implicit derivation, I get 2y times dy to dx equals 3x squared plus 2x, and that is dy to dx is 3x squared plus 2x divided by 2y. And when I try to substitute 0, 0, I get something that is undefined. So maybe another example of a place where a tangent line does not exist. You take this curve and what's the equation for this? This would be just y squared equals x cubed. Here, you may at first glance think that there will be a tangent line simply as the x-axis, because if I take a limit of tangent lines coming from here, then or from the other side, I get the x-axis. But when I examine it according to our definition, I do 2y times dy to dx equals 3x squared. It means that dy to dx is 3x squared divided by 2y, and that's undefined at 0, 0. And indeed, we see this, I think I mentioned last time, the reason that this is not called a tangent line intuitively is that it crosses the graph of the function from two sides. So I would not get into the details of that, but that's one way, one property of tangent lines that it can help you guess geometrically where you have a problem. And okay, so how do we distinguish? I mean, we would like to say that here there is a tangent line, but in this case, and also in this case, there are no tangent lines. So to say that there is a vertical tangent line is equivalent to say that if let me draw it again, over R, and the curve C has a vertical tangent line, say at a point P, if and only if when we reflect C along the line y equals x, the resulting curve has tangent line with slope 0 at the reflected point p bar. And the picture, I will have a hard time to draw it, but in the notes, if you open it, it's at the top of page 68. So let me try, nevertheless.
Is it figure 2, Nathan?
It is figure 2. Yes, exactly. You see, so you have the blue curve, or whatever it is, black, and you have a point P in which the tangent line is vertical, I mean parallel to the y-axis, and when I reflect it along the x, the y equals x line, this is the y equals x line, right? I get, let me try to, I get something like this. Okay, so at this is the point P, and this is the point P bar when I reflect it along the y equals x, and if the purple curve has a derivative 0, basically, I mean a tangent line with slope 0 means that the purple would have a derivative 0. If the purple line has derivative 0 at p bar, then I know that the original white curve has derivative, I mean has a vertical tangent line at the point P. Okay, is this clear? Just the geometric picture. Yeah.
There was a question which is, can we say that we have a tangent if the limit on the left side is equal to the limit on the right side? My intuition was we can, for the example you showed above, in the curve that is blue.
Can you repeat the question?
It's in the chat. Rafael asked it.
Right.
I tried to reply, but I don't know if it's good.
Yeah. No, it's good. But please, in the future, just raise a hand. Yeah, I mean, the definition of a tangent line via limits, it's possible to do it, but I'm trying to avoid it because this would, to make it precise, would take time. I mean, I would at least need to define the notion of a limit.
Thanks a lot. It's just because you show an example where you were going through the curve towards the left and then towards the right, and so it reminded me of the limits.
Yeah, it is. It's true, but this was just an informal explanation.
Yeah.
The formal explanation is, in our case, I did implicit derivation. I isolated dy to dx, and I checked whether I can substitute 0, 0 at dy to dx. Okay, if I cannot, yes.
Yeah, just one question. So here, I don't know because we have two variables, but if we had just one, we can derive again such that we can cancel out the x that it's dividing, and then we have 3x divided by 2 only, if those two were x's. What I'm trying to say is, can we look for inflection points, which is the second derivative, those trying to, how can I say it? Like trying to remove this indetermination, because here you will be dividing 0 by 0, and this is not possible.
I mean, it's true that
I think it's called Hospital.
you don't have to worry about the short answer is you don't have to worry about it, because what we care about is only the first derivative. Whether, I mean, there are like a lot of kind of bifurcations in calculus of trying to fix singularities. I mean, points in which the derivative does not exist. But for us, if it doesn't exist, it's the end of story. We say it's you know, it's a dead end.
Okay, thank you.
So, okay. So what I'm saying here, if I want to formalize it, it would be like saying E of the general form, let's say, has a vertical tangent line at P, if, well, let me put it as a definition, and then if is if and only if dx to dy of P bar is 0. Okay, and you see that this definition is applicable over any field, right? It would be, it's certainly a definition that we can extract in over the real numbers. Over the real numbers, it has a geometric meaning. Of course, the equation of this tangent line, then the equation of the tangent line is, let's call it, we don't need to call it. It would be x sorry, it would be like a tangent line like this. It means that x, yes, x is equal to a constant, which is in this case is x0. Okay, so this, you can think of this equation as a polynomial in two variables, which is in a degenerate form, and the set of all pairs x comma y satisfying this equation is precisely this this dotted line. Okay, so this is how we define vertical tangent lines. I mean, this is how we check if a vertical tangent line exists to an elliptic curve over an arbitrary field. Is this clear? All right. So now that we have all the different definitions in place, let me just make maybe one more, a curve C over K is smooth if it has a tangent line at every point. Okay, and of course this definition is completely meaningful over any field K. And you can guess what is my next step. I mean, we kind of lifted the definitions to the general case over an arbitrary field, and now I want to lift the theorem that told us that the discriminant is non-zero if and only if the curve is smooth. Okay, but I will do it over a general field. And I think maybe it's a good time to take a break here, unless you have any questions.
So see you in 10 minutes.
Yeah, see you in 10 minutes.
See you now.
Hey, can we start again? All right. So the proposition is now as follows. Let K be a field. And C, maybe we call it E. X cubed plus AX plus B, a curve over K, of course. And then delta E, or rather E is an elliptic curve if and only if it is smooth. In other words, delta E is non-zero. Delta E is this 4A cubed plus 27B squared is non-zero if and only if there is a tangent line at every point P on E. Okay, is the statement clear? So how do we prove this? Remember, to have a tangent line, there could be two cases. I mean, either it's a vertical tangent line, or the derivative at the point must be well defined. So I take implicit derivation. And I get the general formula for dy to dx at p. Let's keep the same notation as before. P is x0, y0. So dy to dx in general will simply be 3x squared plus a divided by 2y. This means that dy to dx at x0, y0 is simply 3x0 squared plus a divided by 2y0. So if y0 is non-zero, then the derivative always exists. And if the derivative exists, then we know for sure that there is a tangent line by definition. So if y0 is non-zero, we have a a tangent line at P. Suppose y0 is E0, but the numerator 3x0 squared plus a is non-zero. This means that dx to dy, right, the derivative of the reflected curve, dx to dy is simply 2y over 3x do I want to say it like this? Yes, so this is 2y over 3x squared plus a, and since 3x x0 squared plus a is non-zero, it means that the derivative at the reflected point p bar is zero. So and E has a vertical tangent line at P. Okay, and now we need to handle the last case in which both the numerator and the denominator are zero. So if y0 is 0 and 3x0 squared plus a is also 0. Then necessarily a must be a negative number, right? Because 3x0 squared plus a is 0. And we can substitute instead of a, I substitute minus a, and I get that 3x0 minus a is equal to 0, with a now being a positive number. But of course, this is equivalent to say that x x0 is a over 3 square root plus or minus now I also have the equation x0 cube plus sorry, mine in in our new substitution, it's minus a x0 plus b equals to y0, but y0 is 0, so it's equal to 0. And now I can substitute x0 into this equation. We get square root of a over 3 cube minus a square root of a over 3 plus b equals 0. This is for the plus, for example. And rearranging, I simply get 2a 3 over 2 divided by 3 square root of 3 equals to b, which is equivalent to say that 4a cube divided by 27 is b squared. This is by I take I raise both left hand side and right hand side to the power of 2. And of course, this is equivalent to say that 4a cube minus 27b squared is equal to 0. And now I substitute back a equals minus a, and I get that this is like saying that 4a cube plus 27b squared is equal to 0. So you see, and this is of course the discriminant of E. So do I want to say anything else? Yes. So okay. So so I claim that there is a tangent line in this case if and only if delta of E is non-zero. All right. So this basically finishes the proof. What I was a bit sloppy about here in this in these equations, I wrote square root, but of course, over a general field, we don't have necessarily square root of every number. But you could simply manipulate all the equations. I mean, what you care about is eventually this this expression. And this finishes the proof, right? We have we wanted to show that being an elliptic curve is the same as saying that we have a well-defined tangent line at every point. Any questions about this proof?
I'm a bit confused with the last step, with the conclusion of the last step, when we say that if y0 is 0 and 3x0 square plus a is also 0, then the discriminant is also 0, and there is no tangent line in this case, right?
So yeah, so I mean, to have the last step says basically that to get the condition that y0 is 0 and also 3x0 squared plus a is 0 is the same as saying that the discriminant is 0. So if you turn it over, it means that if you know that the discriminant is non-zero, then this case can never happen. I mean, this case, the case where y0 is 0 and 3x0 squared plus a is also 0 is the last case in which the derivative is undefined, right?
Mm-hmm.
In all the other cases, the derivative is defined. Either the derivative is defined or we have a tangent line. So I'm taking the last possible case in which the derivative could be undefined and also that it is not a vertical tangent line. And I say that in this case, I must have that the discriminant is 0. So if I know that the discriminant is non-zero, then I know I can never get to this case.
Okay.
Okay. So this is the proof over a general field, and I think it's a good demonstration of the principle of what we do here. I mean, we take a geometric notion, let's say from real valued functions, and we try to look for equivalent formulation of the notion we're talking about in a purely algebraic way. And once we have the purely algebraic definition, then it makes sense over any field. And we can then try to turn all the, I mean, at least some of the proofs about properties of this notion that we had in the real numbers to a proof of a general field. And the way to do it is to have completely algebraic arguments. So this is kind of a perpendicular way to analysis. We try to evade all the analytical notions that depends on the specific properties of the real numbers, and we're left with kind of the algebraic content of it. Okay. Other questions? Please raise a hand because I can't look at the chat all the time. Okay. So this was the definition of an elliptic curve. And the next thing in order is the group law on the set of points of an elliptic curve. And again, we are going to follow a similar principle. I think I won't be able to do all the details today, but let me sketch the case, and we get into more details next time. So let's say you have one of these elliptic curves over R, and you take 2 points P and Q. Or maybe let's take P here and Q here. I draw the line between P and Q. Now, there is a general theorem that because this is a cubic, because E is a cubic, then this line must intersect E in a third point, which we can call R. We are not going to rely on this theorem. We are going to show algebraically that there is a third solution, a third point, which is a solution to the line that passes through P and Q and the curve E. So this we can do purely algebraically. And R, let's say, is some x0, y0. And since E is symmetric along the x-axis, I can reflect the point R. So this would be x0 minus y0. And this I call P plus Q. Now, this is not completely satisfactory, because I have some edge cases I didn't take care of. The most obvious edge case is, what do I do when well, you could say that if I want to add P to itself, then I need that I take the tangent line that passes through P. This tangent line will intersect the curve in another point. Let's call it R. And then I take the reflection. Let's call it R bar. This is the reflection along the x-axis. And I simply define R, or P plus P, as R bar. A more interesting edge case would be that, well, if now I take a point P in which the tangent line is vertical. If the tangent line is vertical, then it does not intersect the curve in any other point. So for this, I need to have an additional artificial point, which I call the point at infinity. So this is now the case. Now I have P, and I want to do P plus P. So to do P plus P, I need to draw the line, the tangent line at P. And I need to look for the intersection of this line with the curve. Technically speaking, it does not intersect the curve in any additional point. But if I add artificially a point infinity, which I think is lying at the top of the picture and also at the bottom of the picture. Then this line will intersect, and I now technically include E as include infinity as a point in the curve, on the curve. So now the tangent line will intersect the curve at infinity, and according to my recipe, let's say I take the tangent line, I intersect it at infinity, and then I need to reflect along the x-axis. But to reflect along the x-axis is also infinity. So I get that a P plus P is going to equal infinity. And maybe it's good to make a formal definition. Let E. Yes.
Yeah. So I understand the point at infinity and the previous case with the point R. But do you have any intuition why we are doing this thing? Like, why are we taking the tangents and why are we taking the reflection on the x-axis? Like, how? I guess it all works out in the end because it makes a group and things like this. But it sounds like out of nowhere, basically. Yeah. I mean, yeah.
Yeah. Well, I don't have a short answer.
Okay.
The answer is there are several types of answers. Basically, there is an abstract theorem that tells you that in this situation you always have the structure of an abelian group in this way. But for now, you can, I mean, let's say a more kind of naive motivation is you can always say, I mean, since I have a cubic, it will definitely, let's say in the non-generic, in the non-edge case, I take 2 points, I pass the line through these points, and I know that I must get a third intersection point, right? This point R. Now, okay, it turns out that in order, so I like the what probably people did in the early stages is said, okay, let's define P plus Q as simply R. But that doesn't quite work. But if you instead define it as R bar, you see that you get associativity.
Mm-hmm.
I mean, just as I'm sure that some mathematicians reasoned about it in this way.
Okay, so it's more like So your first answer says there was a theorem that guides how we define the operation, and the second answer is more like try and errors, and then
Yes.
Okay.
Yes. And I think, I don't know for sure, but I think historically it was a trial and error
Yeah.
kind of thing. And later people came with the general theory.
Thanks.
Any other question?
Yeah, I have one.
Yeah.
So you mentioned that all of this is done such that you can kind of map the entire thing as if it was an abelian group. But this confuses me a little bit, because whereas for associativity, having identity and commutativity, I do agree. For the inverse element, I'm not as sure.
Okay, so I didn't define the inverse, but let me first be formal.
Sure.
So suppose we have an elliptic curve, and the set over a general field K, the set of K rational points is this is denoted as E of K. It's the solution set to E. So y squared equals x cubed plus ax plus b. Union the point at infinity. And the point at infinity we actually denote as O. Because this may be counterintuitive, but the point at infinity is going to be our zero element. If you think of it, according to the construction I described, when you want to add, let's say you want to now add p to the point at infinity, then you take the line that passes through p and infinity. You look for a third intersection. So okay, maybe, yeah, I will not jump ahead. What else I wanted to make formal? I wanted to make the inverses formal. So the inverse is very easy. The inverse of R is R bar. Yeah, this I didn't. Yeah. So the inverse of R is R bar. This is the natural thing you would want to do, but by this logic, the inverse of infinity is going to be infinity, because again, infinity we think of it as lying at the top and at the bottom. So it means that infinity is what we want to think about as the zero element. And that's the reason we denote, instead of infinity, we denote it as O. And now you see the importance of the fact that we have a smooth curve, because in this geometric definition, I would need to have a tangent line at every point, because if I want to add the point to itself according to this geometric construction, I must take the tangent line to this point, and then it would pass through another point. I would take the reflection, and this would be Q plus Q. Yes.
So what happens if the tangent line touches in two different points in the curve at the same time?
What do you mean?
So
Yeah, tangent line tangent line to Q.
sorry, at more than 2 points. Apologies, more than 2 points. Two, of course, it touches.
Okay.
So you when you defined the first elliptic curve, you draw one that could have a shape of like this plus a small circle on the left.
Yes.
So if I pick, I mean, I could pick a point such that I touch in this point, I touch in the circle, and I touch in the right-hand side of the curve again.
So we will see algebraically that there would be a unique solution.
This has a unique solution.
This when you take the, I mean, I didn't draw it well. Okay, that's my limitations. But you take a tangent line, right? Tangent line to Q. So in the case of like this. This thing, we will see algebraically. It's not hard that you have. I mean, you take 2 points. There would be a unique, only a third point, only one other point that that intersect with that line, and when you take the tangent line, again, my drawing is very bad, but the answer is that we will see algebraically that there is exactly one solution to it.
Okay, let's look at that. Thank you.
Okay, so yeah, so this is yeah.
So in a way, this point at infinity is kind of a neutral element that's kind of ensuring the closure property on the group.
Yes, and we have to have it because we cannot have any group structure otherwise.
Yeah,
and notice what we say here, in fact, is that P plus P is equal to 0 for this P. So, and this will be true also for, so it will be true for all the points which have a vertical tangent line. Namely, all the roots, these are the points in which you have a root of the polynomial x cubed plus ax plus b, right? So you write this polynomial as x minus alpha 1, x minus alpha 2. You know, this is over the algebraic closure. In this drawing over R, sometimes we have the circle and sometimes we don't have the circle. This depends on how many how many roots of the polynomial x cubed plus ax plus b are over the real number, and not just over the complex numbers. But in any case, so this will be alpha 1, 0, alpha 2, 0, and alpha 3, 0. And according to the binary operation, let's say, that we defined, all of these points, let's say P1, P2, and P3 will be points such that if you add them to themselves, you get 0, or you get the point at infinity.
Are they the same point? I mean, of course,
They're not the same point.
because they are not in the same place. That's for sure. But
Yeah.
what I mean is, it's a bit strange in the sense of it looks like this identity point is not just a point, but like the set of all of the combinations of values that have a particular x and all of the y's, because it's just this straight line of x equals whatever. So all of the y values are possible.
No. Not all the
Oh no,
points
because
in
it has
this
to be
line
there. You're right.
are
Yeah.
on the curve. Only
Fair
this,
enough.
I should have said, yeah, this is P1,
Yes.
this is P2, and this is P3.
That's true.
And they all satisfy Pi plus Pi equals
Sure.
0.
Fair enough.
Okay.
Fair enough. Thank you.
Yeah. Okay, so this is the intuition behind the group law, but of course, if you think of it, the way for me to define the group law, well, we didn't prove it's a group law, but the way for me to define the binary operation was basically through lines and tangent lines. That's all I needed. And this is meaningful over any field. So you could say basically the same definition if you now replace the meaning of a line over the real numbers with what we define as a line over in the affine space over a general field. Then you need to work out the equations to see that some solutions are well defined, but essentially you already have a recipe of how to define the binary of operation over any field. Okay, so this is again repetition of this type of reasoning that we do in algebraic geometry. Maybe it's good to stop here. We can have like a short discussion on whatever questions you might have. Yeah.
It's not specifically a question of that, but about the topic related to the limits that we discussed.
Mhm.
Would it be possible to have some, I don't know, a doc session, or call it what, or do you think it's worth it at least to explain somehow a little bit more for the ones who are interested about the topic of the limits and how to see the tangent from? I mean, if it's pure calculus like Hopital or stuff like this, fair enough, they're not needed. But if it has some more details that are interesting, maybe.
I think many topics in mathematics it could be interesting, but I think it would be too much of a diversion from the material we want to cover. I mean, we want to do algebra, not analysis.
Yeah, fair enough.
And if you notice, I mean, I did mention limits, but I did not rely on it. Because for us the derivative was simply a formal thing. I mean, we only deal with polynomials, and polynomials we know how to derive, right? So you don't need all the theory of limits when you do a kind of formal algebraic derivations of polynomials. Of course, in order to if I go back to kind of justify this picture with the direction vector and so on, you need to eventually go slightly deeper to calculus and define the derivative as a limit. But that's the only thing. It's so if you accept this as given, then I mean, you don't need anything else in this discussion.
Makes complete sense, Matan. Thank you. Thank you very much.
All right. So yeah, what I'm not sure how to proceed exactly, but I will reserve it for next time. The issue is that to prove explicitly the associativity of the group law would be a very tiresome task. And what I think is we could do some cases, but not all of them. But we will see next time. All right. So